Have I told all of you that I'm a beekeeper?
Yes.
So something's about to start happening soon. Inside of a beehive, you've got a whole bunch of bees crowded together. They like literally snuggle like shoulder to shoulder, stay warm at night and through the winter when it's cold. Since it's too cold and crummy weather for them to go outside and find food, they eat their regurgitated nectar. So during the year, they drink nectar and they barf it into these little cells, and then they cover it for later. We call that stuff honey. It's their nectar barf. It's super concentrated flower nectar. That's why each type of honey tastes different, because it's nectar from a different plant species. So anyway, in the winter, they all sit inside and drink all their honey and shiver to stay warm and to keep the queen warm. But if they're really crowded, they start to give off like a stress pheromone, and the queen's ovulation changes so that she'll make a few weird larvae that instead of growing up to be drones or worker bees, will grow up to be new queens. Now, usually, the queen walks around and kills them. But if it's so crowded that she can't find and kill the queens, one of the other queens will realize, wait, there's another queen around. They smell each other, and they go fight. And all the other bees are like, Mom, Mom, stop fighting, Mom. And they go, wait a minute. And they have too many queens in there. And so they'll grab one of the queens and drag her away from the fight and fly away with her to go start a new hive somewhere else.
Dang.
The crowding triggers the production of the additional queens that will fly away with the crowd. That happens technically throughout the year, but not much is notable until the first warm days of spring, which I predict are any day now. Some of you noticed we just had an actual cold snap in Santa Barbara. It's been a couple of weeks now. We've had night times getting down into the 30s even, which for Santa Barbara is horrifically cold. And as soon as we get like 2 or 3 warm nights in a row, the bees are going to start swarming. What you see is a big cloud of bees that'll probably settle onto something that looks good enough. I've seen them on mirrors on a car, on the chain of a bicycle. I've seen them in like waist-high landscaping. I've seen them on a big piece of driftwood at the beach. A bee swarm first looks like a cloud in the air and then looks like a gigantic water droplet of like swarming bees. Just so you know, when they're doing that, they're super peaceful. You can trick the bees into swarming, and when you trick them into swarming, they go into mellow mode because they just want to keep it cool around the queen. You don't want to fight because the queen is exposed. So instead of stinging, they go mellow. You ever seen the people who wear bees all over their bodies, or like in Ripley's Believe It or Not, or the circus, like the beard of bees? Those are all swarm bees. So when you see that big teardrop of bees, don't try this at home. But if you're gentle, you can pretty much just grab that huge ball of bees and just walk away with it. And they'll like crawl over you, and you're just like a billion bees in you, and they won't sting usually.
How do you get
Will Africanized bees still sting?
Oh, you know, around here, all bees are kind of Africanized, and even Africanized bees are much mellower during that swarm thing. So, these are both sliding scales, how Africanized and how safe they are. Technically, you gotta be really gentle, and there's like a few tricks about temperature and colors and facial hair. Can't look like a bear. They sting me no matter what. Because they think I'm a bear. Or rather, they know I'm a bear. I ask that all of you, please let me know if you see one of those teardrops of bees somewhere that's kind of accessible, maybe 10 or 12 feet off the ground max. On the eave of a roof is nice. In trees that are like on flat ground, not too high is nice. There's no way to get a hive out of something without massive demolition. So if they're like in the deck or like in the wall or like in a stump, like I need chainsaws and hammers and like tools to get bees out. But if there's like a big glob of bees, which I think is going to start this Saturday, please call me and I'll drive over and I'll bring an extra bee suit if you want to try. And we will capture all those bees. And the day after, I'll come back and drive them away. Are there any questions about this bee thing? Yeah?
How far away should I put my other box? Should I like set up the other box?
3 feet.
3 feet? Okay.
Facing 90 degrees off.
Okay.
You don't want them to get confused about which way they go in. So all of your current ones go in from the side facing the house / facing the front fence.
So
You want the other one to be like 90 degree to that, so they come in from your backyard side, from like the barbecue area. You can even go 180 degrees, so they come in like down the fence, your neighbor's fence. That would work.
yeah.
Anybody else? Yeah?
So if you grab the bees, how do you get them off you?
You shake them. It's like when you have like water on your hands and there's no paper towel.
And they won't like, oh,
Or a towel?
dang, this is like, they won't think that this is like a bad situation trying to sting.
I can't guarantee what the bees are gonna think, man. Despite knowing that you can touch them, I've only done it on a dare to show people that you can touch them, but it was kind of nauseating and I didn't really want to do it. They're still all vibrating and they still all have stingers. And as soon as one of them goes nuts, all the other ones go, what, we're attacking? And then they would all go for it. So I've never really wanted to start that party, you know. Yeah. But I've done it. I showed my children. I was like, look, you can kind of, yep. And I like lifted up like the big teardrop and I put my hand kind of into it. And I took my hand off and there was 2 on my hands now. And my kids thought I was the coolest dad in the world. I was like, I'll never have to do that again. All right.
With the Queenie scooter, we had like nothing was happening in the top box, and the bottom box got like super heavy. Is that?
So none of them went to the top box through the Queen excluder?
There's like a few bees that were like walking around. But
When did you put the Queen excluder in there?
it's a long time ago. More than 5 months.
Before Halloween?
Yeah.
We should probably just look at it.
Okay.
Anybody else? Water use inventory and post lab are due tomorrow. Now let's talk about that field trip. How many of you stayed with the sub? Anything I need to hear about yesterday, the substitute events on campus or other? I am not self-conscious. I'm actually just curious about how you decided. Those of you who stayed. How many of you stayed because you were discouraged by the crowding of the previous field trip? How many of you stayed because there was something on campus that you had to do yesterday, so you just could not go on the field trip no matter what, whether or not you wanted to? And how many of you, given the choice, just kind of thought, you know, I don't really want to spend my day doing the field trip tomorrow? It's okay, I'm just curious. So mostly it looks like it was a campus conflict. For those of us who went, we had like a really relaxed, leisurely, low crowd field trip. There were empty seats on the buses. We went up to Schofield Park, Rocky Nook Park, stayed in Alomar, Oak Park. We went to the ditch over between Mission and Pueblo. And then we went down to the river mouth over at the ocean. We saw a bunch of stuff along the lines of number 24. Please take that out now. Are we done grading the Unit 6 exam? Are we done grading it? No?
No. I think there's still a lot to do.
Whole, huh?
The whole, yeah.
Will you give me a period by period, question by question breakdown? Yeah.
What's on me? I'll do that in a second.
You know what's cool? Yesterday's example, even though it hadn't rained in 7 weeks, was kind of perfect. We got to see kind of exactly what I wanted to see. Of all the stuff I told you about, we pretty much saw it all. Pretty much. And of the problems with canals, we could kind of imagine the stuff that we didn't see. So those of you who were here on Friday last week saw the comparison between rivers and canals. Then we went out and we saw that. So now I'll tell you what we saw. Here's what we saw. Definitely shade rocks, gravel, sand, deep, shallow, fast, slow. Pools, riffles, little spills. And that habitat diversity was really clear and obvious. You could pretty much see everything. We definitely saw riparian vegetation, stuff growing above, along, on the way to, and even in the river. At Rocky Nook Park, all the kids were standing on top and I went down to the creek and I was like walking around between the rocks and we saw like sandbars of built up sediment from the water slowing down the year before with all these greens sprouting through it. Like a plant nursery effect. I talked about today, which I'm not sure I've mentioned enough in class, and so I'd like you to add something. That our landscape, our soils, the vegetation, they work like a huge sponge. At the first stop, I told all my students to be quiet because I could hear the water, and most of them were just a little further away, so they couldn't hear it. But we were sort of far above it, so I could like hop around and look down into the water at Schofield Park. But the students, they were kind of up on the bank. I don't think any students were able to actually see water running. But I realized yesterday, it's been almost exactly 2 months since the last rain. You know, it rained last night, but yesterday morning it had been 2 months. And you would not have any water in canals. Canals are built at a very subtle angle, so the water pours over. And when the water runs out, it all goes away, and then you're back to a dry canal. And we saw that. All the canals that we visited were dry. But up in the first couple of stops where we were in the wilder part of the river, there was water flowing. Not like a ton of water, it wasn't rushing, but there was moving water everywhere. And I thought that's kind of neat, because the land works like a sponge. And 8 weeks later, there's still water migrating across bedrock, being exposed in that riverbed and pouring past our field trip yesterday. That's a big deal. When I tell you that wetlands extend water flow, that they moderate flooding, and then keep it coming over time, that's how. Sponge, bedrock, trickle 8 weeks later. I thought that was neat. That's something that we saw on our trip yesterday. The way that the landscape works like a huge sponge, so that wild rivers tend to have a lot more water flow over longer periods of time than creeks. Sorry, the canals. We talked about food web complexity, about how native plant species benefit native insect species, which all have relationships to native amphibians, fish, birds, mammals. It was crazy. We went from uphill to downhill, and that also went from a lot of bird species to like a few bird species to like 1 or 2 bird species to like no birds, and then the beach. I thought that was actually pretty interesting. It's possible that birds sing less later in the day. But I think overall there was a distinct pattern of food web complexity going down as we went downriver to the city. You know, something that we did not discuss on Friday, you may want to add, is that natural rivers are also accessible to migratory fish. Because natural rivers have extended flow of water, that sponginess gives them extended flow of water. Those migratory fish can keep finding a way up to where they breed. I'm speaking specifically of salmon, really. Those salmon can find a way upriver 1, 2, 3, 4, 5, 6, 7, 8 weeks after each rain, because there's still a little bit of water that they can jump from pool to pool. As long as they get to a big pool, they can wait. Up by the Natural History Museum, they can circle and circle and circle and circle, and I've seen them there. That's pretty cool. Right where the rope swing is, before you turn up to APS and stuff. In that pool, they can just circle and wait and wait and wait and wait, and the next storm comes and they do the rest of the swimming. Because, you know, habitat diversity, high dissolved oxygen levels, you got some shady spots, they can chill. So migratory fish can make it up natural rivers. We also talked about how bioremediation is like a thing that's actually kind of simple and you can imagine. I can't remember who I chose, but we were all standing in a cluster like this, and if I said, if somebody over there were to go pee right now, if Sean Dolan were to go pee right now, I said, that would not really join the river as pee. Because in this distance, like from me to Amore, there was like a tree right there and a tree right here and some shrubbery against the rock over there. There was a bunch of grass in the way. I said, you know, in that spongy soil, you'll have microbes breaking that down. You'll have plants absorbing the water. You'll have a variety of soil chemistry reacting with the salts. If any of that water or any of that material were to get washed later down to the river, that'd still be pretty clean. Because most of that stuff gets bioremedied. Stuff in life will change and use up that impact. So happy. It is a good life. It is a good life, children. Thank you for pulling that off. We talked about how water was probably soaking in through the ground and improving our groundwater supply. You know, let me point something out. When I talk about recreation, I guess what I mean is like whitewater rafting industry and fly fishing guides and stuff. On the AP test, if they ask about the value of real rivers, you can say that they support tourism and recreation. But there's something else that I'd like to point out. And everybody who didn't go on the field trip, I don't know if I can convince you of this, but everybody who went on the field trip, I'll bet you know what I'm talking about. Being in nature just plain old feels good.
Oh, I felt so much more focused.
I did too. I mean, like, I get so stressed by stuff that isn't that stressful. Like, I'll have this thing like, oh, I gotta check the time. I gotta check the time. How many minutes do I have left? I do that like every 7 seconds or so. Like, oh, I gotta check my, there it is, press the button on the phone. Press the button on the phone. 10:36, okay, press the button on the phone. I'm like, yeah, where did that was a person. Where'd that person go? Somebody snuck away right there. And like all this lighting and all these corners. These weird sounds. Your brain's always filtering. Like, ooh, what was that sound? Is that a threat? But I don't know. We were out there yesterday on the creek, and I pointed out to my students that when humans go out into nature, almost any single way that you can measure human stress levels, as far as you can measure it numerically, stress goes down in the wild. Pretty much always. Like if there's a lion chasing you, okay, that's pretty stressful. But by the way, it's a healthy type of stress. It's short-lived and it spurs action that saves your life. Here, we just live and it's like, oh my God, who just came through the door? What is that? Is it an active shooter? No, it's probably, okay, cool. It's probably, nice. You weren't there, but I did this thing where I told my students, like, take a second and let that soak in and like listen to the sounds and feel and like you're like breathing better. And like your oxygen saturation goes up, so your heart rate goes down, so your blood pressure goes down. And with like all of those variables, your like focus abilities go up and your digestion goes up. You heal faster, learn better, remember more. I love all that. I really don't know how to say that on the AP test. So I'm not sure you should say that unless you have a way to say it accurately enough. But I've added it to the board. It just plain old feels good to be there. You could say that some humans have a social or cultural or religious or spiritual connection with wilderness. And those are all real words that are probably accurate if you use them in a full sentence, I mean. Then when we got to the canals, I could pretty much show you all of this, but not everything. In big drainage canals, you get these temperature spikes. Imagine when the sun comes out over this. Please look up. When the sun comes out on the LA River, that water gets really hot really fast. So there's something I could not show my field trip students. I couldn't show you the temperature extremes. In Santa Barbara, our canals are actually pretty small, and there's still vegetation along the edges, so they still stay pretty breezy and shady. That was kind of nice of them. Hello. Thank you. Amor, it is convenient for me that you go to ASB whenever you want. It says at teacher's convenience, so you can do whatever you want. Yeah, you don't have to go. Okay. Well, it was very easy to show my students the absence of habitat diversity. It was very easy to imagine if there was water that it would have been stagnant in most parts of those canals.
Stagnant and still, right?
We could certainly see how ecological complexity was generally trending downward as we went downhill. It was tough to know if it would have been aerobic or anaerobic. But especially in larger canal systems, you can imagine that the still water wouldn't have a lot of dissolved oxygen. You could see how the water would have dissolved oxygen levels up in the creek, though. When we were up higher at Rocky Nook, you could just see these little babbling little ripples and like little bubbles, and the water looked all clear and lovely. There is something that we did get to see on the field trip that's nowhere in your notes, and it's not in your book that I'm aware of. These are nice for migratory fish because there's pools and riffles and the water stretched out over a longer period of time, and so the migratory fish, by which I usually mean salmon, they can go upriver in a real wild natural river. But not in most canals. In a canal like this, you wait a day or two and that water's gone, and all of a sudden it's impassable to wildlife. So please look up. Wild rivers are okay for migratory fish. Canals are usually impassable. But Santa Barbara has something cool that I don't think is in your book anywhere. We have one salmon-safe channel. Mission Creek is unique. There's almost none of these on the planet. Very, very few. Mission Creek is a concrete canal that would be useless for salmon most of the year, except we spent gazillions of dollars making in the middle of the canal a deep spot that creates eddies for the fish to rest, and it creates pools where the water is slowed at these temporary mini dams, so that it kind of makes like little puddles one after the other, and the salmon have better chances of getting through the low elevation stuff before they hit the pools up at higher elevation. Santa Barbara spent a bunch of money to be unique, so that we would have more passable canals. That was neat. That was really cool. I'm glad that I can show you that.
There were like huge boulders stuck in the water.
Yeah, you can tell how powerful that water is in flood water because of the boulders that have moved. And you can tell how eddies are formed because they all settled outside the main line in those little eddies. Yeah?
Are canals and channels the same thing? You use them interchangeably?
Yes.
Okay. And then also, how do you define channelization?
To make a canal? Okay. We did not get to see the wastewater facility. I wish we'd been able to, but the remodel has made it impassable to field trips. We did get to see one final bonus right at the end. It occurred to me, oh yeah, you can see all the sponginess that we experienced at the beginning, and when we were down at the bottom at the river mouth over by the pier, we looked up at the hills, and from the ocean, if you haven't done this, it's kind of a perfect opportunity, like right now, today in particular, like this one Tuesday in the afternoon. Go down to the beach, look up at our hills, and you'll see this big green swath of chaparral that terminates somewhere around Parma Park-ish. And after that, the hillside looks distinctly different. And you can see where there's this shift between the spongy chaparral and the non-absorptive fire scar that caused that big mud flow in January. That was really neat to see that from the ocean. I mean, obviously really scary and really serious, but it was also kind of an interesting thing to have such a clear contrast. I'm glad we could do that field trip, and I'm sorry that some of you couldn't make it, but I guess you got the majority of the content and you just missed the experience of seeing it. Anybody want to talk more about the field trip, or are we done with the field trip talk? Yes?
No, I had a question.
No. Please take out assignment 7.3.
Why is channelization practice so expensive?
Because it's a good way to manage floodwaters. They do prevent floods.
Okay. What's the printer?
You're gonna pull Wi-Fi?
Yeah.
This is not it. It's none of these. There's a difference between like AirPrint and wireless printing or something. I don't really understand this distinction. I can do it from your phone, but I can't do it from that.
Oh, you can?
I think so.
Oh, okay.
All right. Vocab on assignment 7.3. Yeah?
Landscaping, I guess, bioswale, and then the inadvertent, direct, and indirect water reuse.
I think that the landscaping is a type of landscaping, right?
I don't know.
Close
It's-
loop.
Yeah, closed loop landscaping. So that's landscaping where you don't have to add water or material.
And then bioswale.
A man-made wetland, artificial creek.
Okay. And then inadvertent, direct, and indirect water reuse.
So direct water reuse is where used water gets to be used again. Like the way that I water with gray water at my house, that's direct. In a very, very, very few parts of the world, wastewater is used directly as drinking water, like on the space station or like shuttle expeditions. You know, the astronauts pee and sweat and all that gets filtered back in the water. Here in Santa Barbara, we direct reuse about 30% of our wastewater for irrigation of schools and green belts and city parks. That's direct. So it comes from the plumbing of the wastewater facility to a spigot somewhere. Indirect is like what they want to start doing in Irvine, where they're taking all the wastewater and instead of reusing it directly, they just pour it onto the surface. It recharges groundwater, and so then they extract the groundwater. That has been filtered by the earth, and so that's indirect. But you know that your groundwater includes a significant bonus of wastewater that's treated. Does that make sense? Indirect. It goes back into the wild for a minute, and then you collect it again. And inadvertent is when that same thing happens, but you didn't manage that system. Like somebody upriver puts wastewater in, and then you extract your drinking water when you're somewhere downriver. Like if you think about the Mississippi, there's people who draw their drinking water from the river, and you know that you're kind of using somebody's wastewater because upriver, God knows what's gone into that river. Yeah.
Sorry, for closed loop, you said landscaping if I don't even add
What?
water.
Sorry, for closed loop, you said landscaping that you don't have to add, but then I didn't get like the last
Water or material. Yeah?
For what is it, eutrophic?
Yeah?
Is that when there's just
I'll show you. I want to do a study goal.
added?
I'll show you. I'll show you that. Okay. Let's do some study goals. I'd like to point out that our thing from block day, from Wednesday, was misnumbered. Some of you caught it, some of you did not. Nobody told me until this morning. But if you numbered it 26, that's wrong. Apparently it's number 25. That's my numbers from last year. Organic waste, decomposition, oxygen supply. So you already got number 25. 26 and 27 are kind of easy. Please look up. I need you to add something to your notes because your book has one type but not the other type of eutrophication. So first, 26 and 27, I'd like to talk about lakes. Most lakes are at high elevation, and so they are what's called oligotrophic. Oligo or oligotrophic, which means low nutrients, like this. Not much nutrients, because how could you have much life going into the water? There's almost no life uphill. Anybody been at moderately high elevation, 8,000 and up, hiking above Mammoth, backpacking in the Sierra, climbing in the backcountry? Those lakes are basically pure water. You know, don't take that as a promise. But fundamentally, they are all oligotrophic, which means they have very few nutrients because they're so high to tree line that there's really nothing to donate organic material and nutrients for life, so they're pretty lifeless. They might be frozen for much of the year. Then they just have snowmelt and very little other inputs of organics. Lakes tend to be oligotrophic. And the type of problem your book describes is when lakes have too many nutrients. That's called eutrophic. If you do it, it's called eutrophication. Eutrophication makes them eutrophic. This can be natural, we'll talk about that. But usually we blame people. We'll talk about that too. And your book talks about what happens to lakes. Because lakes don't have a lot of water movement, you add a bunch of nutrients and usually that will fertilize algae at the surface. It's called an algae mat. And if you did your homework assignment, you know that the algae mat filters sunlight, so you get a big layer, like a spa cover, of algae on the top of the water, and then you have a blackout in the rest of the lake underneath, so less producers, less insect activity, less fishy activity. So there's the algae mat problem in eutrophic lakes. But your book told you everything I just said, so I don't want to waste any more time. Are there any questions about the lake stuff? Anything that you need to clear up with me? Because there's a whole separate problem that's much more interesting, I think. What happens in oceans? This is maybe more about 27 than 28. Sorry, more 27 than 26, excuse me. More 27 than 26. When you dump a whole bunch of nutrients in the ocean, listen carefully because there's a lot of confusion. The first thing you're going to get is good news. Extra nutrients in the ocean is fertilizer to life, is a burst of productivity, is a good thing. Algae bloom. This is not a problem. When you get more algae going off in the water, you know what else you get? More plankton eating that algae. Then you get more little fish eating the plankton, and more medium fish eating the little fish, and more big fish eating the medium fish. Please look up. If this is your trophic pyramid, fertilizer expands the productivity, which of course expands the consumer levels. Does it make sense to everybody that if you fertilize the ocean, you get a big old life party? Many of you have experience with this. The problem with having a party is not the partying, it's the cleaning up at the end. In the ocean, nutrient levels rise, productivity rises, consumer activity rises, and it's just big old disco. Problem is, when those nutrient levels start to drop off, now you've got less algae, which means you've got a bunch of starving plankton, which means you've got a bunch of starving little fish, which means you've got a bunch of starving big fish. And as things start to die, you get into this cycle. So let's see if this diagram helps you write the words in your notes. Maybe if not, you can interrupt me. But imagine I'm somewhere back here. In terms of time. So at one time, you fertilize the ocean. And then, it's a big old party out there. And then, the nutrients run out, and everything starves. Now you understand a rise in decomposition will use up the oxygen, and you can get what are called ocean dead zones. This is really bad. Your notes should probably say nutrients, smiley face, life party. Nutrients run out, frowny face, decomposition, oxygen sag, anaerobic water, dead zone. When I talk about lakes and rivers and oceans, for me, I have experiences with lakes and rivers and oceans. So for me, I just visualize these are different places. It's like all of you athletes talking basketball and then football and then other sports with balls, baseball. You know that there are different behaviors and different rules and different athletes and all that crap. Well, these are different systems. So we've talked about what happens in rivers and streams with nutrients and dead zones. She's absent today. Thank you. And then we talked about, your book talks about nutrient loads in lakes and stuff. Now, talk about the ocean. All big rivers have seasons. That came up when we talked about dams. Which means all big rivers have high flow and low flow. When any big river has high flow, there's going to be a big burst of productivity outside that river. So if you go outside the whatever river that is, or if you go outside the Congo or outside the Amazon or around the Rio de la Plata or outside the Colorado River or the Columbia River, naturally you get spikes of productivity and die-offs at the end. That's natural. But imagine a very special case like the Mississippi River. I'm not sure that this has occurred to you, but the Mississippi River is globally unique. It has some of the most intensive agriculture on Earth, plus some of the biggest population numbers contributing to that river anywhere on Earth. Because think about how many people add to the watershed of the Mississippi River. Plus it has some of the worst urban runoff on Earth because it's a big old river that includes a bunch of factory towns and a bunch of old cities. And now please imagine that when they have their flood season, those nutrients spill into warm, still ocean. Look at the Gulf of Mexico. It's practically shut off from the ocean. You see that? The Gulf of Mexico is surrounded like 320 degrees and then blocked by an island for the rest of the 40. So the Gulf of Mexico is largely isolated. And during the wet season, the Mississippi dumps a lot of nutrients. So the worst ocean dead zone on Earth is the Gulf of Mexico. They get these gigantic bursts of life, and you get these crazy algae blooms, and the fish go nuts. Oh, fishermen get all psyched, and they go out there and kill tons and tons of fish. And then you wait like 2 months for that water to taper off, and you can like see it sometimes. Like science dorks will send those deep sea submarines, and there will be like decomposing mounds of sea life. And you know, it's a snowball effect, right? More stuff dies, more stuff decomposes, more oxygen's used up, so more stuff dies, so more stuff decomposes. Positive feedback. I've seen pictures of like ships cruising through the Gulf of Mexico through these huge slicks of dead fish, which all die at once on the surface because the water goes anaerobic all of a sudden. You know, it's like a tipping point, usually triggered by temperature or wind. And there's a special thing that happens sometimes in those dead zones, not always, but sometimes, where you get a flush of algae that just happens to be bad for you. Those are called red tides. It's a generic term because there's one type of algae that is bad for you and also makes the water look red. It literally is red in the ocean. Yeah?
Sorry, how did you define red tide?
It's a bloom of algae that's hazardous to life. Hazardous algae bloom. Most algae blooms are not hazardous. There's one in particular that I find really intriguing. If you're ever bored, you should Google this. Pfisteria piscicida. Like fish side, you know, like kills fish. And I don't think it's technically an algae, but anyway, it's some sort of phytoplankton. It kills fish. It makes fish toxic, so humans eat them, and then humans die from fish poisoning. But check this out, one of my favorite things in biology. In very rare cases, Pfisteria piscicida will go into a reproductive phase all at once, and they shoot these spores into the air. And usually those dissipate, but if you have like a very particular mix of ocean temperature and air temperature, there will be like an inversion system where like low air will trap all that near water level. And sailors and fishermen will navigate through those waters, and they inhale those spores, and they all die, and it makes these things called ghost ships. And apparently, occasional blooms of this phytoplankton are responsible for a lot of the mythology about evil mysteries in the ocean. Because the spores, if concentrated, are toxic enough that everybody on the boat just like dies on the spot. So you'll be like navigating through the seas, and you pull up on a boat and you look inside and everybody's dead. And like, huh, maybe there's monsters out in the ocean. And like apparently like the parts of the world that had most of the mythology about mysterious evils of the sea are parts of the world that would support red tides and have the right water chemistry for this species to survive in the oceans there. Red tide is a generic term. And I gotta be really clear about something. Can you all visualize the United States, please? If I fly over the United States sprinkling fertilizer, is that all going to make toxic life grow more? Think about it. If I drop a whole bunch of fertilizer on top of corn, I'm just going to make corn grow more. And if I drop fertilizer on the redwoods or the pine trees, it's going to make more conifers grow. And if I drop all that fertilizer over like palm desert, I'm going to make more golf course grass grow. Because that's a good place that we decided to put all of our golf courses. It makes good sense. But you know, if I drop fertilizer on nightshade, well, nightshade is technically toxic. You still got to figure out how to get it in your body. But that fertilizer would cause more nightshade poisoning events. Because I fertilized nightshade by coincidence. Right? It's coincidental. Most of the plants are not toxic inherently. Fertilizing doesn't make them toxic. But if you fertilize toxic species, you'll get more of those toxic species. Is that clear for everybody? So red tide is coincidentally that stuff which is toxic becomes more common. Has anybody heard that there's like mussel and oyster closures sometimes? You're not supposed to eat shellfish in months that end with R? Anybody heard that? It's a thing. You're not supposed to eat shellfish in months that end with R. Yeah, it's a thing. Can anybody put that together now that I mentioned red tides? Months that end with R? Shellfish? Yeah.
Is it like, because a lot of the R months sort of end, or are in fall and winter.
September, October, November, December are the months that end with R. September through December. Does that help anyone?
And so like that would be like when like the first storms would be coming maybe?
In our part of the world, that's right. That's why here you don't eat those. And what's that got to do with anything?
And then huge nutrient dump into the ocean and
and all of the naturally occurring toxic algae are going to become more common. So your oysters and your mussels, which are filter feeders, will have elevated levels of toxins because when you fertilize the ocean, you get more life, and some of that life might be bad. And you know, just to play it safe, you don't eat the mussels and the oysters during the months that end with R, because their toxin loads go up because you fertilize the sea, and that includes some things that are bad for you. For a couple of years there, those same things were building up in crabs. So you might know that last year there was a closure on crab fisheries, or 2 years ago there was a closure on crab fisheries. All right. Please look at study goal number 28, because that has the easiest answer ever. Does anybody know the 4-letter answer to what are the main sources of waterborne pathogens like coliform bacteria? You can answer this in 4 letters. Poop! That's right. Yeah, there's also a naughty word that is 4 letters, yeah. So pretty much coliform bacteria comes from fecal matter in mammals and birds, to a lesser degree birds. Coliform bacteria is present in basically all the mammals. And I've already told you this before, but I want to revisit your notes to make sure you put it in the right place. Coliform bacteria is anaerobic. So usually poop and water is not a problem because usually water is aerobic. See? High levels of dissolved oxygen. We got our eutrophication, we got our dead zones, we got our poop. I'm going to stop here so that we leave a few study goals for next time. We're going to do saltwater intrusion, wastewater treatment, a few fast study goals. We got a block day coming up. Get ready for the next exam. We'll do the stars on Wednesday. We'll talk a little bit about the post-lab. Water use inventory.
is